All right, so what we want to do today is I want to go ahead and talk to you a little bit about energy and electric fields, we'll say, energy and E-fields. And in particular, thinking about the work done by the electric force. So take a look at this. First thing I want to talk about is start about work. And so you would say, hey, I remember that we have this base formula for work. That work is the way that energy is transferred in or out of a system. The work done is the amount of energy that gets transferred. And then if I want to do work on an object or transfer energy, that requires a force from outside the system to push through a distance. We have an equation for that. That work is force through a distance. Now, if I had a nice constant force pushing a nice constant angle, then I can write that as like a force pushing through some change in position. Now, I'm going to use R to be like a general, distance vector. I know some people like to use an S if it's like an arc length. We can talk about dx, dy, dz, talking about our delta x, delta y, delta t, talking about a particular axis. But I just mean in general, whatever the path is, that force, we take the part of the force that's parallel to the motion times the distance it moves and pushes through. That dot product, remember there's a cosine theta hiding in there, and then we really want that angle there. That's what determines the sign, positive or negative of the work. But anyway, we've got this. So let's apply that now to an electric field, right? If I had some nice, maybe uniform electric field. So here I'm drawing my electric field lines. I'm making them nice and evenly spaced and have them all going the same direction because remember, that the spacing of the field lines tells you something about the strength of the field. And I want it to be the same electric field strength everywhere for our example, for our first example. Say that I want to move a charged particle from here, we'll call that location A, to here, location B. And we'll say, well, my charged particle, let's make it a positively charged particle, okay, a little positive Q. And we'll say, while it moves from A to B, you say, hey, that electric field would be pushing on that charge. There'd be an electric force shoving on it. And the electric force, say, well, I remember the E field lines, the electric field lines, they always show the direction of the force would be on a positive charge. So I can draw my force vector in like this. My electric force would be pushing that way and would be moving that way. And so I could calculate that work done. I'm just going to say, hey, the work done by that electric field would be the electric force dotted with the distance we push through. And so the work done by the E field, you say, well, I'd really like to get this equation in terms of electric field strength. We just spent a whole unit calculating electric field strength, that capital E. So let's do this, let's rewrite this equation in terms of big E. So you say, okay, well, I remember electric field strength. The way we calculate that is we say, well, imagine I have a particular location and I want to think about how big the force would be on a charge that was put there. You say, well, how big the force would be, it depends on how big the charge is. So instead we talk about the force per unit of charge that we put there. My newtons per coulomb. So the electric field strength, remember, is the electric force per charge. And this is the value at a particular location, right? So if I rearrange this, I would get that electric force would be the charge times the field strength. So that's what I'll substitute in here for Fe. So my work done by the E field would be equal to the charge that's getting pushed by the field strength, dotted with the distance through which it acts. And so that's my formula. But when we make that substitution of QE in for force, it actually can cause a little problem. The dot product here, remember that there's a little cosine theta hiding in that dot. That we're just looking at the angle between the direction of the force and the direction that we're moving. And if they move in the same direction, it'd be cosine of 0 degrees, and I get a positive workout. If it pushes against the motion, I get a negative out for the cosine. Well, when I did this substitution, look, I just swapped it out. So now it's not talking about the direction of the force necessarily. It's talking about the direction the field is going in. Now that's okay if you have a positive charge, because the way the field goes is the same as the way the force would be on a positive charge. But what if you had a negative charge? The force would actually be going the opposite way. If I wanted to move, if I had this charge moving from here to here, the field would be pushing against the motion that whole way, right? If I had a negative charge, the electric force would be to the left, and it would be pushing against me as I move an electron here, move a negative charge there. And so that electric field would be actually trying to slow down the charge, taking energy away. I need to get a negative work out of that calculation. But the E field is going in the direction of the motion. So the way you fix it is you need to make sure that you do include the sign of the charge that you're moving around. If I was moving a negative charge, that negative in the Q would fix it and make this be the correct sign. Make my work come out to be the correct sign. So last unit, when we did Coulomb's law, and we talked about the force between charges, you may remember Q1, Q2 over R squared. You may remember that when we have two charges, we said, wait a minute, these two positives would repel each other. I'll have an electric force going this way here, and an electric force going this way here. You see, this equation can't tell you both directions at the same time, right? Whether a force is positive or negative, it tells you direction, but it can't do both at the same time. So we recognize that this equation can only tell us the magnitude, the size of the force. It can't tell us the direction. And so whenever I use this equation, I always just use the absolute values of the charges and recognize this was just going to tell me the absolute value of the force, the magnitude of the force. When it came time later on to plug into F equals ma, to start adding vectors, then I would need to put the sign on it myself. Force is right minus force is left. I'd be putting that sign, that negative sign on myself for direction. It's not something built in the formula. That's the way it was with last unit. We would always put the sign on for direction ourselves manually. Well, now, in energy calculations, you do include the sign of the Q. All right, and that's something to remember. All right, it's a big deal. So, moving onward. Back to this. So we came up with an equation for the work done by a uniform electric field. But what if we had a slightly different situation? What if I had some great big charge here, right, making an electric field around itself. Right? And maybe I want to move a little charge in that field. So you want to go from position A to position B. And I want to move my little charge here, this little q, from here A to B. You say, well now, as it moves along, if I try to do this work calculation, I have a problem. The E field strength is not the same here as it is here, as it is here, as it is here. The electric field strength is different at all those points. So what value of field strength do I use? Use the field at the start, the field at the end, the field from halfway through? Well, we know that what we would end up doing, the way we would solve this problem, is you say, well, I recognize that E is changing as I go. So what I might do, if I use the value at the start and use that for the whole time, I see the field's getting weaker as the field lines get farther apart. I'm going to end up with, too much work done by the E field, because the E field is actually getting weaker, wasn't doing as much work. So what I might do is just split this into two chunks. So I'll look at the motion from here to here, and then with the E field strength from here, and then from here to here, using the E field strength from there. Is that going to give me the right value? And then add up the work for the two parts. You say, well, no, that's still going to be too much work, because again, it wasn't that value as it kept going, it was getting weaker than that. You say, but it's going to be an answer that's closer to the right answer. So maybe I'll chop it up into more pieces. The E field here for this distance, the E field here, calculate here for this distance, for here for this. It's going to be a value even closer to the right answer. What I'm going to have to do is chop this up into a whole bunch of little pieces. How many little pieces? An infinite number of little pieces. Each little push through a distance, force through a distance, force through a distance, force through a distance, force through a distance. That's work, right? And I'm going to have a whole bunch of them. So what I'm going to do is I'm going to talk not about the total work, I'm going to talk about the little bit of work done by the E field through one of those little pushes. That'll be equal to the charge and the E field strength at that point times a push through that little distance, dr. I do a little bit of work by pushing that charge in that field through a little distance. I'm just going to use the E field value right at that spot. And then I go an infinitesimally small bit further over, and I do that same thing again. I do a little bit of work applying the E field there through that little distance, and the next little bit. And then I'm going to add them all up to get the total work. If I add up all the DWs, that's just the total work. This equation, Q is a constant. I'm not changing the charge size as it moves. I can move that, I can factor that out of the integral. This is going to be my equation for the work done by an electric field. And this will apply even if my E field is changing as I go. I can still use this. By the way, when does this equation turn into the simpler version? When am I allowed to use the simpler version? Well, if that E was constant, right, constant field strength, then it might move out, right? But also, don't forget, there's a cosine theta hiding there. That angle between the E field strength and our motion has to also be a constant. So if that E and that cosine theta are constants, then these would move out, and the integral of delta r integral of dr would just be delta r. So it would turn into this. Okay, so that's the special case that lets this turn into this. But this is the general formula. This is the formula for the work done by an electric field. How much work an E field does shoving on a charge that's moving through the field. All right. So we've talked about that. Let's go to, we talked about the fact that the charge matters, so the sign of the charge matters, so you got to include that. Okay, let's go to the next bit. Right, so let's say that we're going to move this charge, okay, and let's make this a little more exciting. Instead of going from A to B right along the field line, let's go to, say, some position up here. Call that position C. Let's say we wanted to go from A to C. All right? Well, you're like, that's okay. This electric field on the positive charge would still be pushing parallel to the field lines. That's the way the electric force is. While this thing moves that way, that electric field will do some work. That force, it has a component parallel to the motion, and that's fine. We would be interested in doing that calculation. Field strength dot the path, right? That path we're taking, that direction, that displacement we're going. You say, and look at this angle here. That would be my theta, the angle between the force and the motion. And I'd be doing that force cosine theta. Now, what I want to point out here really quickly is about dot products. If I have A dot B, that's A cosine theta times B, right? You say, and I'm going to do absolute value, absolute value, yeah. But the point is, did you know that when we do a dot product, the order doesn't matter? Because what would B dot A be? Just BB times cosine theta times A, right? You know what I mean? And it's the same thing. I just rearrange the order. It's the same thing. With dot products, the order doesn't matter. With cross product, it does. With dot product, it doesn't matter. And so we thought about the work equation in the past. We thought about like pushing on something and trying to speed it up. We said, hey, I really just care about the component of the force that's parallel to the motion. So when we do this calculation, we said it was like we were taking just the component of the force that was parallel to motion. Here's our perpendicular component, making a right angle here. See, it was just the part that was parallel that mattered, and that would be that force times the cosine of theta would give us this side, right? This is the hypotenuse here. That would give us this side. I'd take that part of the force times the distance we push through, right? That was the way we thought about it. But you could think about this another way. Instead of thinking about taking the part of the force parallel to the motion times the distance it pushes through, we could think about the part of the path that's parallel to the force times the force. Because isn't that what, if I'm doing F dot delta R, I can think about it as being delta R dot F if I want. You know what I mean? The part of the path that's parallel to motion. So here's my change in position, and I take the part of this that's parallel to the motion. This length, or that's parallel to the force, I should say, times the force. We'll get the same answer out. Think about it this way. Notice that if I go from here to here, I could think of that, instead of doing this direct line path, I could go horizontally and then vertically here, right? Jump to get from A to C. This part of the motion, this part here, you notice that when I'm going across the field lines, the electric force is parallel to the field lines, right? Is that electric force doing any work along this part of the path? No, it's perpendicular to the motion. If I did a dot product, it'd be cosine of 90, and cosine of 90 is 0. It's not, the electric force, while I go from B to C, it's not making me get any faster or get any slower. It's pushing sideways to the motion. It's only this part of the motion that mattered. The part that's parallel to the way that force is, the way the field is, that's the part where work was being done by the E field. So we can think about it that way. But this brings up another important idea. And that is, wait a minute, to get from A to C then, I could calculate with this and use my cosine theta and all that, or I could just take this and this. This path will take me the same amount of work done by the E field as this path. In fact, it turns out I could take any path to get from A to C, and it'll be the same amount of work done by the E field, regardless of the path I take. I mean, think about it. What if I did a path like, this? And then I go, and you say, no work done there. E field's pushing perpendicular to the motion, doesn't do any work. And then I do this, What if I go past it, and then I turn around and come back and end up there? Wouldn't the work done through this part and the work done through this part balance each other out? Here would be positive work done by the E field, and then negative work done by the E field as it pushes against me. You say, that motion of that positive charge. And so you say, hey, this would just balance out. I'll get the same answer out as if I just went there. Not every force works this way, that it does the same amount of work no matter what path you take to get from A to B. Forces that do work that way, we call them conservative forces. And what's special about conservative forces? We can write potential energy functions for them. And potential energy functions are so useful for calculations. So that's what we're going to do here. We can write a potential energy function around the electric force. So how are we going to do that? Well, let me show you. We remember, hopefully, this idea from back in the energy unit, that if I have one of these conservative forces and I can calculate the work it does, then I can figure out the potential energy change. We say we have this idea that the work done by a conservative force, whatever it is, if I took that and I flipped the sign on it, that's the change in the potential energy that's associated with that conservative force. For example, with gravity, we say, look, if there's the ground, if I have, a rock, and I want to lift the rock up from position A to position B, right? So we're lifting it up. You say, while I'm doing that, you say, if I'm going to lift it at a nice constant speed, so I'm not changing its kinetic energy, all the work I'm doing is changing its potential energy. But you say, as I move it up there, you would say, hey, gravity is pulling down. The earth is pulling down the gravitational force on that rock. It's pulling against the motion. The work that the gravitational force is doing is negative here. How much work does it do? Well, that force through that distance. But what if once I got it to B, I let go? Now gravity could pull on it from B back to A and to apply that force through that distance, but now I'll be doing positive work on the rock, speeding it back up. And so the amount of energy, basically, I'm putting into the system when I lift it up here, pushing against gravity, that's the amount of energy I'm going to be able to get back out again when it falls, turn back into kinetic. If I look at it, they say, on the way up here, gravity is doing negative work. When it falls back down, gravity will do that much positive work. I'll get that much energy back out. What happens if instead of analyzing the rock as my system, what if I include the rock and the earth? Well, now that force isn't on my diagram anymore. because it's a force inside the system. If I do the rock-earth combined system. And so now, if I push the rock and the earth farther apart, if I let go of it, now it can fall through that distance and get all this kinetic energy. Where did it come from? It must be from some energy that was stored up in it. And that energy stored up is that gravitational potential energy. So that's the idea. I just calculate the work that the conservative force, in this case gravity, did against me. If I flip the sign on it, that's how much energy now I can get out of it again when that gravity force pulls back down and falls back through. You see, I look at the work that conservative force did, flip the sign, that's how much energy we just stored up in there. So what I could do here now is I could write this equation for electric force, right? And for electric potential energy, I have an expression for the work done by the E field. I'll just take this guy and put it in there, flip the sign. And so if I do that, I'll get negative Q integral E dot dr, and that's my change of electric potential energy. Okay. The energy I've stored up. Right? That's a pretty sloppy integral sign, Dave. I don't know if that's that much better, but there you go. All right. Okay. Okay, let's go a little bit further with electric potential energy. First of all, let's make sure that we are still on board this idea of electric potential energy. If I had, what is potential energy anyway? We talked about it being, every potential energy has a certain force, a conservative force that's associated with it. You have potential energy when you have a system that has a couple of objects in my system, and there's one of these conservative forces acting between those parts of the system. And if I rearrange that system, then I change how much work that conservative force could do, hypothetically, inside the system. But what I'm doing is then I'm changing the amount of energy stored up in the system because of that force between the parts. Say, take this. If I have these two positive charges and I set them down there and let go, what would happen? Oh, well, they would like repel apart. And as they repel apart, they would go faster and faster and faster. I'd be getting all this kinetic energy. Where from? From energy stored up in the system. For having these two charges near each other in this arrangement, I've got some energy stored up there. Energy is the ability to do work. It's the ability to apply a force through a distance. If I have these guys here, when I let go, they could repel. They could shove on other objects. As they repel each other, they could push other things. They could apply a force through distance to things. They could do work. So there's energy stored up because of this configuration of charges. So that's potential energy. Energy because of configuration. So there we go. So tell me about this. If I have these two guys here, what if I go ahead and I let these guys move to be a little bit farther apart? Does this situation have more potential energy or less potential energy than this system? More electrical potential energy or less electrical potential energy? Which one's, you say, what's going to happen here? Well, we're saying that these have potential energy because when I release them, they could repel apart and they could shove at other things as they repel. These guys, they're farther apart, but they're going to still repel and shove other things. But will they be able to push through as much distance as these guys could push? These guys are able to push through more distance than these guys are, right? There was more energy stored up here because they can push through more distance. Try this one. If I wanted to have these guys move from this arrangement to this arrangement, will they do that on their own, or will I have to apply a force to get them to go from here to here? So no, they would naturally want to move that way. If I set these guys down and let go, they'll naturally move like that, and they'll move further apart. Okay. If I want to go the other way, if I have them farther out and I wanted to move them closer together, I would have to push against that electric force to squeeze them closer together, right? I would have to do work to go from this arrangement to this arrangement, which means I'm having to pump energy into the system by doing work on it against that electric force. It turns out, if you ever want to increase a potential energy, you are going to have to push against that force that's associated with that potential energy function. If I've got a spring and I want to, it's a spring at rest, and I crush the spring down. As I'm crushing that spring, the spring force is pushing against me, isn't it? And I'm storing up. When I let go, it'll go zing back out again, right? You say, hey, I'm always pushing against the spring force to increase energy. What if it was at rest and I pull it out? Well, when I'm pulling it out, the spring's pulling back against me, trying to bring it back to its rest length. And you say, so I'm doing work pushing against that spring force. You say, it's always that way. With gravity, I got to push up against the gravitational force to increase gravitational potential energy. If I go down, I lose gravitational potential energy. So that's a better way of thinking about it, a nice way of thinking about it too. So if I'm going to be increasing electric potential energy, I'm going to be moving things against the electric force. Okay, good idea. Good enough, good enough. Okay, which brings me to the next bit. All right. What we came up with here is an equation not for the electric potential energy, but for the change in the electric potential energy. All right? We would like to come up with an equation for electric potential energy. Let me show you what I mean. If I have these two charges here, right, we know that there's some potential energy stored up. Having these guys some distance apart there, let's call that distance r. Okay? This is the field made by this big cube. Say I have those two charges, and they're this distance r apart. All right? And so you say, well, if they're this far apart, there's a certain amount of electric potential energy stored up. What I want to do is calculate just the UE for this arrangement. This guy and this guy that far apart, how much energy have I got? So I need an equation for that. I don't know if you remember, but we did come up with a general technique for finding potential energy functions. We said, go back to this. If I'm doing, this is a calculation for a change in energy, right? But I really want energy at a position. So here's what I'm going to do. That deltas always mean to take the final minus the initial, right? So this would be like my UE at some final location minus my UE at some initial location, right? And I'll just, if I can calculate the work, which I have equations for, and flip the sign, then it gives me that. But what I don't really want a change in U equation right now. Right now what I want is just a way of calculating U for a particular arrangement. So here's what I'll do. You'll recall that for every potential energy function, it has to do with the arrangement of some particles. We always pick some, or objects, we pick some arrangement to say that when it's arranged like this, in this configuration, we'll say the potential energy is 0 for this arrangement. And then we'll compare to that. Do I have more energy or less energy stored up? Does that make sense? So for this case, with charged particles, what arrangement would make sense to say this is the arrangement where they have 0 potential energy? If you think about it, you'll recognize that it's probably not going to be just someplace out in random location here in space. You say, well, it seems to me like the other options are, what if they were like right on top of each other? Or what if they were infinitely far apart, right? Or anything else would just be somewhere random in between. Well, on top of each other is really not going to work. We talk about this whole idea, like, can two objects occupy the same space? You're like, well, when you get to quantum mechanics, it gets goofy. But the point is, if I think about like Coulomb's law for force, because I'm going to be interested in looking at that force from the E field, right, and figuring out, you know, as the distance objects get infinitely close together, right? And I start talking about that electric force and how strong it is and how much work it could do. You're like Q1, Q2 over R squared. Like, look, as R heads to 0, this shoots up to infinity. And you're like, well, I don't want to call where the force is shooting to infinity and trying to calculate the work done by that force that's approaching infinite. You say, that's going to be a mess. What if they were infinitely far away? Well, then the force would be 0. That's a nice spot to say is 0 potential energy. And so that's the way we will define it. We'll almost always say that when charges are infinitely far apart, we'll assign that to be the 0 potential energy arrangement. That's kind of cool too, because the force between them will be 0 there, and so moving around a little bit doesn't do anything. That makes sense. So that's what we'll do. So we define UE at r equals infinity. These guys are infinite distance apart. We define the UE to be 0 at r equals infinity. So here's the trick now. If I want to find an equation for UE, not delta UE, what I'll do is I'll do this calculation. But cleverly, we'll either start the object or end the object at a location where U is 0, because that'll make that term drop out, because U is 0. And I'll get an equation just for U. Just for U. For the U, and what I'll do is I'll be even more clever. And what I'll do is maybe I'll go from at infinity, where the potential energy is 0, and I'll think about it. I'll move it not to a particular location, but to some generic general variable distance r. So I'll get an equation here for that potential energy when I'm at r minus my potential energy when I'm at infinity. Do you see that? So as I move my charge from out here at r equals infinity, where UE is defined to be 0, right? And I'll move in to here at r equals r, and the UE at r, that's what I'm going to find. Okay? And so I'll get the general term. This will drop out. So that's my plan. All right? So let's do that then. All right? Let's do this calculation. I'm going to skip down a line. The work done by the E field, that's this. E dot dr. Delta UE, that's my UE at r, which is what I'm trying to find, minus the UE at infinity. I'm going to go from infinity to r. Does that make sense? But this is 0. So I'll get my equation for UE at any position r. It's a variable position r. Great. Okay, hey, here it is. Now for this case, you say, I want to do this calculation for the work done by this field as we move along. Do I have an equation for that field? Actually, you know what? Even before I do that, see that dot? Let's resolve that dot product right now. All right? That dot means there's a cosine theta. Now, if I'm moving from infinity to r, I'm moving this way. My path is this way, but the E field is this way. That angle between them, that's 180. So this is going to be a cosine of 180 in this case, right? And cosine of 180 is just a -1. So remember when I take a dot product, the only sign is from the cosine. So I need this whole calculation here, where I'm adding up all these dot products, all these little pushes through little distances. This whole bit here must give me a negative value, all right? Because the only sign is from the cosine. So whatever happens when I'm doing the calculation and doing the integration and all that jazz, whatever I get for the sign, at the end, I need to make sure that this is negative, okay? Because the only sign is from the cosine function, right? Now you notice over here, that's going to cancel with that negative and give me a positive at the end, okay? But I'll let this hang out for a little while, all right? So don't forget about that. The sign for this chunk here has to end up being a negative. And I will manually make it so if I have to, okay? Because of that cosine 180. All right, so working through. So I do my integral where it says E. Do I know the E field strength? You say, yeah, this is a field made by a point charge plus Q. I can write the equation for an E field made by a point charge plus Q. If I had a different shape here, well, that's for another day. A point charge here. So you say, okay, so the E field made by a point charge, I know what that is. That's just KQ over R squared. This is E field from a point charge. We know that formula from last unit. I've got my cosine 180, right? And then dr. Evaluating from infinity to r. Okay? Whoops. And this is the delta UE, but it's not delta UE, it's actually UE at r. Let me move that to the other side just so it's out of the way over here. That's my UE at just any position r that I'm trying to find. All right. All right. hey, when I do this integral, anything that's a constant can kick out of the integral. What have I got here that's constants? K and Q and cosine 180. They come out. So I'm going to have negative K, Q, Q. You say, no, wait a minute. That cosine 180, that was a negative 1. That'll cancel that negative. My answer at the end is going to be a positive. I got the integral now of 1 over r squared dr. And you say, hey, I feel like I can do that integral. The integral, this is like r to the minus 2 power. Take the integral, it would go up a power, it'd be r to the minus 1, or 1 over r. It would technically kick out a negative, though, right? Negative 1, right? Integral of r to the negative 2 is negative 1 times r to the minus 1. Okay, and I want to evaluate that from infinity to r. When I do that, I'll get a negative 1 final minus initial, negative 1 over r minus negative 1 over infinity. You say, well, 1 over infinity, that's just 0. So I'm getting a negative 1 over r. But remember, I need this integral thing here to come out to be negative. I already did the negative from the cosine 180. I should have waited another minute to do that. And so I'm basically going to ignore that negative. You know what I'm saying? Because there's really, we're doing like absolute values here. So what I'm ending up with then is this is just going to be a 1 over r. Is that integral? So I got, what I end up with then is just k, q, q over r. That is my electric potential energy for those two charges r distance apart. That's the formula. Okay. That's energy we have stored up. As r gets bigger, these charges get farther apart. They've got less energy stored up in them, right? Now, for general notation, we usually don't call them big Q and little q, because it didn't matter that this was big or that was little. It just mattered which charge I was moving. I'm just going to call them Q1 and Q2. Okay, and that's our formula for electric potential energy. Now, when you look at this, you may say, hey, that looks really familiar. That looks a lot like the formula we came up with for gravitational potential energy. We looked at two masses, and we had a little mass way far from planet. We talked about the energy it would take to maybe push it out to infinity. This case, I went from infinity down to r. But the point is, when we did that calculation, you might remember the UG equation came out to be G m1 m2 over r. Just like this KQQ over r, but there was a negative sign there built in. You remember we said when they're infinitely far apart, they have zero potential energy? Because these things want to attract, as they get closer, right, they're losing potential energy. And since objects are always closer than infinity, or with zero, it's always going to be a negative value, the gravitational potential energy for a system. Remember? But with this, if I got two positive charges, it's the opposite. They want to repel. And so if I push them closer to infinity, I'd have to do work to shove them closer, be putting more energy in the system. I'm going to have more than zero energy if they're both positive. But what if one of these is positive and one of these is negative? If I start them infinitely far apart, we're still going to say that's the zero energy arrangement, but positive and negative would want to attract. And as it naturally attracts in, it would gain kinetic and lose potential, right? It would have less energy than at zero. So if one is positive and one is negative, I need to get a negative answer. And that's okay. That's what I'll get if I put the signs on the cube. And one is positive and one is negative, I'll get a negative answer out. It'll be like the gravity case, where I have negative energies that get closer. If I had two negative charges, negative times negative would make it positive. Does that make logical sense to you? If I had two negative charges, if I start them at infinity, the energy is zero. If I wanted to push them closer together, I would have to do work because the two negatives want to repel each other. My energy would go up as they get closer, and that's exactly what happens if you put the signs on the cubes. So that's the way that works. Okay, I've got one more thing to share with you here, okay, about potential energy, electric potential energy. Before ending this video, I'm going to save electric potential, which is something else, and voltage for next video. The last thing I want to share with you is this. We now have an equation that we can use to find the potential energy for a system of these two charges that are r distance apart. Okay, this k, lowercase k, that's the Coulomb's law k. You say, well, that's great. So if I have a couple of charges, here we go, look, there's Q1, and there's Q2, and there's some distance apart. That's R between 1 and 2. I can calculate it. Okay, Q1, Q2 over the distance between 1 and 2. But what if I brought in another charge? Look, there's Q3 now. To have these 3 charges near each other, there's 3 that are going to repel each other, right? There's more energy stored up here than if there was just 2. I would have to do more work to push all 3 charges in from infinity near each other. Can I calculate the energy stored up in this system of 3 charges? Well, we actually did a similar calculation with gravity for 3 masses, right? What I recognize is potential energy exists because there's a force, the conservative force between the objects, right? And I have to push against that force to increase the potential energy, with it to lose potential energy. You see, if I bring in a 3rd charge, what I'm introducing is 2 more interactions. These guys are going to interact, and these 2 guys will interact. And so I'm going to have 2 more terms. K, Q1, Q3 over the distance between 1 and 3, and K, Q2, Q3 over the distance between 2 and 3. Okay? So I'm going to end up with 3 terms. Because there's 3 things interacting electrically, I'll have 3 different potential energy terms in my equation. Okay, for the total UE. You say, what if I brought in a 4th one? If I bring in a 4th charge, that would introduce 1, 2, 3 new interactions, so I'd have 3 more terms. I have 6 terms in my equation. If I brought in a 5th one, I'd have 4 more terms. I'd have 10 terms. Anyway, we're good with this, yeah? That's the way that works. Okay, so really my UE, this is the equation for 1 pair, potential energy of 1 pair of particles are apart. And you say, what if I brought in more? I'd have to have more of these terms. 1 for each interaction. All right, and that's it. Okay, so that's introduction to work done by an electric field and electric potential energy, energy stored up in a system of charges. Sometimes when we talk about this, by the way, instead of talking about, it's really these charged particles, that system of particles that has the energy, right? One particle doesn't have electric potential energy by itself. It only has it because the other guys are nearby, right? So it's something the system of particles has. So we have defined systems for energy calculations. We want to be careful about that. But what I want to point out is sometimes we'll talk not about the charges repelling each other. Sometimes we'll talk about the field that they make. And this guy being pushed by a field. And we'll talk about energy being stored up in an electric field. Okay, and sometimes we'll talk about it that way. Just a side comment. Let's talk about energy stored in the field. We'll do more with that in a bit. Okay, that's it for this one.